1. What a transformer is. Basic parts. Core, a laminated ferromagnetic core that guides magnetic flux. Primary winding coil connected to the input, supply, voltage. Secondary winding coil that delivers the transformed output, voltage to the load. Insulation, tank, bushings, cooling, mechanical and safety parts for real transformers. 2. The basic physical principle. Transformers work by electromagnetic induction, Faraday's law. An alternating current, AC, in the primary winding creates a time-varying magnetic flux in the core. That changing flux induces a voltage in the secondary winding. 3. Step-by-step operation, ideal transformer. 1. AC applied to primary. When AC voltage is applied to the primary winding, an alternating current flows, limited by the circuit and the winding impedance. 2. Magnetization of core. That alternating current produces an alternating magnetic field, flux, in the ferromagnetic core. 3. Flux links windings. The core guides most of that flux, so it links both primary and secondary windings. 4. Voltage induced in windings. According to Faraday's law, the instantaneous induced voltage in a coil is proportional to the rate of change of flux and the number of turns. For sinusoidal steady state, we use RMS values. \frac V_P V_S is equal to \frac N_P N_S. 5. Turns ratio decides voltage. If the transformer is step-up, secondary voltage higher. If it's step-down. 6. Load draws current. When a load is connected to the secondary, current flows and that produces its own magnetic effect in the core. The primary supplies the magnetizing current plus the current needed to balance the load via mutual coupling. 7. Power transfer. Ideally, electrical power minus small losses is transferred from primary to secondary. V_P I_P \approx V_S I_S. \frac I_P I_S is equal to \frac N_S N_P. 4. Simple numeric example, step-by-step arithmetic. Suppose turns, and primary RMS voltage V. Turns ratio. Voltage ratio. Compute. Work digit by digit. So the secondary RMS voltage is 46 V, step down by factor 5. If the secondary delivers 10 A, ideal primary current is equal to A. 5. Real-world behaviors and losses. Real transformers have non-ideal effects. Core losses, hysteresis, and eddy current losses in the core depend on flux density and frequency. Copper losses, I2 are losses in the windings when current flows. Leakage flux, some flux doesn't link both windings, causes imperfect coupling and voltage drops under load. Magnetizing current, a small current needed to establish core flux even with no load. Noise and heating, magnetostriction causes hum, cooling, oil, fins, fans, manages heat. 6. Important operating features. Efficiency, transformers are usually very efficient, 90–99% depending on size and load. Tap changers, used on transformers to slightly vary turns ratio to regulate output voltage. Impedance, winding impedance limits short-circuit currents and affects voltage regulation. Frequency dependence, designed for a specific frequency, example, 50 Hz or 60 Hz. Operating at different frequency changes flux and losses. 7. Types and uses, brief. Power distribution, large step-up at generation, step-down near consumers. Isolation transformers, same turns ratio but provide galvanic isolation for safety. Autotransformers, single winding with tapped output, smaller, lighter but not isolated. instrument transformers, current transformers, CTs, and potential transformers, PTs, for measurement and protection. 8. Quick checklist to visualize. AC into primary alternating flux in core induced voltage in secondary load draws current primary supplies that power through magnetic coupling.